Hello my dear students. So today we will be discussing the continuation to the last class, the colligative properties, and first we will discuss about depression in freezing point, then next we will be discuss about abnormalities in their molecular weights. Since we know that colligative properties are number dependent properties, it depends upon number of solute particles. Okay, so now if a species, if a given electrolyte undergoes association or dissociation, then there exists some difference in the number of particles of that solute right now. So this causes the difference or the abnormality in their molecular weight. Okay, so we are going to learn that. First of all, let us discuss about depression in freezing point. This is the last colligative property we have. In the last sessions we have discussed RLVP, delta TB, elevation in boiling point, next osmotic pressure, and now depression in freezing point. Okay, so here, so what exactly depression in freezing point? See, the name itself saying there is some decrease in the freezing point of that particular solvent. For example, see here what exactly freezing point. First of all, understand that, later we will move forward. See, freezing point is the temperature at which vapor pressure of the solute, vapor pressure of that particular liquid will be becomes same as that of solid phase. It means vapor, liquid vapor pressure, solid vapor pressure will be in equilibrium with each other. This is the state, or this is the temperature at which we are considering it as the freezing point of that particular liquid. Okay, so now here what happens, the decrease in the freezing point of a solvent by addition of non-volatile solute is known as depression in freezing point. Let us say I have a graph here, vapor pressure versus temperature. Okay, so here we have a graph. So now I am drawing the graph for vapor pressure versus temperature for solvent. So when I have a pure volatile solvent, consider this kind of scenario you will be seeing. Okay, so maybe this kind of difference you will be seeing here. So now see, here I have highlighted one point over here. So this point represents, this is a point where liquid and the solid phase of this solvent, this is for solvent graph, okay, curve, solvent curve. Okay, so this is the point where liquid and solid are in equilibrium. So now I can say this temperature, the corresponding temperature here, I can say this as freezing point of solvent. Yes or no? This is the point where freezing point of solvent is considered, because there exists equilibrium between liquid and solid. Yes or no? Hope it is clear. See, we know vapor pressure increases with temperature, that's why graph is looking like this. As temperature increasing, vapor pressure of this component is also getting raised. Okay, right now look at here. Now what I am doing to this solvent, whatever present here initially, we have only solvent, we are drawing a graph for vapor pressure versus temperature for this solvent. Now what I am doing is, I am adding some solute. This solute is non-volatile solute. When non-volatile solute is added, freezing point of solvent by addition of non-volatile solute decreases. What happens? Decreases. It means this point further moves downside. It means this freezing point of solvent is there, na, that moves this side. So it will be comes around, for example here, after adding solute to this solvent, what happens? It becomes solution now. So let us say somewhere it is coming like this, something like this. So this point is what now? This is a point, I can say, see where this point we have solid and liquid are in equilibrium. Further this is for solution. So what we can understand from this, the solvent freezing point is further suppressed or decreased. Okay, so this is the temperature, I can say TF of solution. Okay, it means freezing point of solution. Now see, there is a difference right now. So this difference I am representing it as delta TF. So this difference delta TF, I can write it as final, see the higher value is TF naught minus TFS. It means the depression in freezing point delta TF is equals to freezing point of solvent minus freezing point of solution. S represents solution, here not represent pure solvent. Okay, hope it is clear up to here now. Yes, if it is clear, just click on the like button. Now this is the first thing you need to know here. So look at here, So Ts is freezing point of what? Solution. So how this freezing point of solution and depression in freezing point are related? See, more delta Tf, lower is the freezing point of solution. Why? Because see, there is a negative sign. So they are something like inversely related to each other. This, if depression in freezing point is more, the freezing point of solution should be smaller. That is what the difference we are making means what? See, if this value is smaller, then what happens? Difference will be becomes more, right? Like that. Okay. So it is decreases, it is increases. This is a relation. I am highlighting this because when you are going to solve the questions, you will get to know the importance of this small understanding. Okay. Now I will be telling you few other things. Now delta Tf is a depression freezing point of solution is directly proportional to molar concentration. What is that? Molar concentration. I can say molality. Okay. Now I am removing this proportionality and it will become Kfm. So what is this Kf? So this is a depression molar cryoscopic constant, I can say, or molar like depression constant, I can say. Okay. So more specifically sometimes it is mentioned as cryoscopic constant also. So now what is the unit of this Kf? See here, the unit of this Kf, if someone asks you how can you derive this, Kf equals to delta Tf by m. That's it now. So delta Tf is nothing but Kelvin is a unit for delta Tf, and for mole this is molality, mole per kg. So what I can write for Kf units as degree Kelvin multiplied with kg per mole. This will be the unit of Kf. Okay. Now Kf, the value of Kf depends upon only solvent, nature of solvent. This depends only upon nature of solvent. Already we discussed the same story for delta Kb also in terms of in case of elevation in boiling point. Same points applicable here also. Okay. Hope up to here it is clear. Okay. Now let us look one question also here. Let us understand one question also. See, this is a graph we have discussed right now. So now what is the other thing we need to know is, see, delta Tf equals to Kbm I have written now, right? So Kbm is molality. I can write Kb into molality means what? Number of moles of solute by weight of solvent in kg. Okay, it should be in kg. If it is in grams given means you can write it as Kf, here Kf into Nb by weight of A into 1000 here. Right now you can take weight of solvent in terms of kgs now. Now number of moles also I can write Kf into weight of solute. B represents solute, A represents solvent here. Okay, and weight of solvent into here number of moles I can write weight of solute by molecular weight of solute into 1000. Okay, so this is the equation which is also very important. Okay, and now we will be solving a question related to this. Okay, now move forward here. Read the question. 5 grams of a substance when dissolved in 50 grams of water lowers the freezing point by 1.2 degrees. Calculate the molecular weight of substance if the molar freezing point depression constant Kf is given this much. Very easy. The given data contains number of moles of solute. How much they mentioned? They haven't mentioned this. Weight of solute they have mentioned. Weight of solute is mentioned. They are asking molecular weight or molar mass of the solute. They are asking us. Okay, this is the thing they are asking. See, delta Tf value is given now. Delta Tf equals to Kbm, Kfm we can take. Okay, so now delta Tf value is 1.2 degrees given. So this value is mentioned. So molality I can write number of moles which is weight of solute by molar mass of solute into weight of solvent into 1000. In the last page only, here only I have written this equation I am taking here. Okay, now this is equals to delta Tf. Everything is mentioned except this. Okay, that is what we need to find. So molar mass of solute will be equals to Kf into delta weight of solute by delta Tf into weight of A solvent, that is into 1000. Yes, by substitute the values, now you will get the answer. So Kf is mentioned as 1.86. Okay, so into what is the weight of solute mentioned? 5 grams. Okay, and delta Tb is mentioned as 1.2 into, and the next what they have mentioned, weight of solvent mentioned as 50 grams. Take here 50. into 1000. Okay, so 0, 0, 5, this one also cancel. Then what we are remaining with? So here 6 2s are, okay, this is 0.2 and this will be 0.31. Okay, so I can write this as 31 or 310 by 2. So this will be 155 gram per mole. So this will be the answer for this particular question. Hope this is clear now. Yes, yes. Shukla, Shreyan Shukla, I am looking into the chat box. You can write it. Okay, you can express your concerns. Hope this is clear how we are solving. Right? Yeah. So now just give a try again without looking at the answer. So just try to solve this very basic question I have given. Okay. Now let us move forward with the other topic. So now write abnormal molecular weights. So when we will see this abnormality in molecular weights, so we have studied all the colligative properties. If you see all the formulas, we got RLVP, delta TB, delta TF, and next osmotic pressure, everything. All of these are what? Now these are what? Inversely proportional to molecular weight of solute. In every case when I am discussing these colligative properties, I have explained the relation. We are finally concluding it as molecular weight of solute. So it is inverse of reciprocal, we are getting a proportional inverse like proportionality like this. So RLVP, for example, I am taking just now we have seen a delta TFC. Here delta TF, just check here, see delta TF, depression in freezing point, is inversely proportional to the molecular weight of solute we got here. Similar to this, every time in all these colligative properties we are resulting with this thing. Okay, so it means we know these colligative properties are number dependent properties now. If a substance, so when we see this abnormality means when a given substance, let us say electrolyte, in substance or especially electrolyte undergoes dissociation or association. Now what happens? The abnormality in molecular weight is found. So why it is found? Because when a solute, for example, when first condition, let us say when dissociation happens, what happens? Dissociation happens. So dissociation happens. What happens in this case? So for example, I have a particle, for example NaCl is there. So initially when we look it like this, it looks like only one particle now, but when we place this NaCl in the aqueous medium, it will dissociate like Na plus and Cl minus. So I am generalizing this. I have a particular component A. Okay, so when it is undergoing dissociation, I have a particle of n times like this. Okay, so it dissociating means it will become a power like some charge, it will be getting like this. Okay, so now from this what you got? See, it is dissociated like n times it is dissociated right now. So initially we have only one particle and this is 0 at a time initial at the beginning. So after some time what happens? This particle undergone dissociation. Let us say alpha is the degree of dissociation, and here we got n alpha number of ions from this particular electrolyte. Okay, so now what we can understand from this? So total number of particles after dissociation, how many particles we have? This is 1 minus alpha plus after dissociation, see 1 minus alpha plus n alpha. This many number of particles are formed after dissociation. Okay, so from this I can write 1 plus n minus 1 alpha. We are talking about dissociation, let us indicate with alpha d. Okay, so these are the number of particles after dissociation. Okay, see initially we have only one particle, but after dissociation we are getting 1 plus some particles, right? Now 1 plus this term is there. It means after the dissociation number of particles increasing. Right now if number of particles increases, so colligative property values also increases. It means the values of this RLVP, delta TB, delta TF, pi also increases. Okay, if these are increases, its observed molecular weight from this colligative properties will be decreases. Since I increases, these particles are increasing, all these terms will increases, therefore molecular weight decreases when we calculate using this colligative property. So in order to avoid this confusion, in order to avoid this abnormality, so Van Hoff introduced a factor called Van Hoff factor, indicated with symbol I. Okay, so symbol I. So how do we give this? See, so for example I am writing RLVP. So what is the formula we can say? RLVP equals to number of moles of solute, okay, by, like we are writing like this now, mole fraction of RLVP equals to, so like P naught minus PS by P naught is equals to mole fraction of solute we are saying. So mole fraction of solute means number of moles of solute by number of moles of solute plus number of moles of solvent. Like this we are writing now. So wherever you have solute particle, because solute only undergoing dissociation and association now, there you introduce value of this I. Okay, so wherever you have number of moles of solute, wherever you are seeing solute, there you introduce this I value. So what is this I? So Van Hoff factor I is equals to number of particles after dissociation by number of particles before dissociation. Okay, number of particle before dissociation, like this. So for example, NaCl is there. Now we know this is strong electrolyte. It has alpha value how much? Alpha value like 1. Why alpha value 1? It 100%, almost 100% dissociation takes place for this. So it gives us Na plus Cl minus. Right now, so number of particles after dissociation, how many we have? This is 1 and this is second one. So I will be 2 by, before dissociation we have only 1. So I value for NaCl will be 2. So it means if you are calculating RLVP or delta TB or osmotic pressure for this NaCl solution, you have to use this I value. So here delta TB also there now. So kbm we are using initially. Now you have to introduce this I over here, and delta TF also you have to use I into kfm. Okay, and for delta TF is also over. Next pi will becomes I Cm RT or Cm ST. It means molar concentration multiplied with Van Hoff factor. Okay, so for NaCl you should take it as 2. So now for a strong electrolyte, what happens to this total number of particles? This is a formula you should remember. Okay, so for alpha equals to 1 for strong electrolytes, so it becomes 1 plus n minus 1 into alpha d is there na, that is 1. So our I becomes this one is cancelled, I becomes equals to n. Okay, for this is alpha equals to 1 means 100% dissociation, it means 100% dissociation. Okay, okay. Next, hope this discussion is clear. It will be more clear with 1 or 2 examples. Let me tell you, see let me show you one question otherwise. Look at this. Which are the following aqueous solution will exhibit highest boiling point, they are asking. So how do you calculate this? See, we have concentrations like this, given like this. We need to express which is showing highest boiling point. So just take delta TB equals to I kbm, just now I told you. Okay, right, and here delta TB I can write TBS minus TB naught. TBS is nothing but boiling point of solution minus boiling point of pure solvent, which is equals to I kbm. So higher the I value, if you see, higher the I value, greater is its elevation in the boiling point, I can say, and increase in the boiling point of solution, I can say. Okay, so you take the product of these 3 terms, the one which is having high product of these 3 terms, that will be your answer. Okay, look at here, we have Na2SO4. So it is a strong electrolyte now, it gives us 2 Na plus ions plus 1 sulfate ion. So what is its I value, total number of particles after dissociation, how much? So I value is 3, see 2 plus 1, 3. So in this case, this is a non-electrolyte. For non-electrolytes, take I value 1. For glucose, urea, sucrose, all these are non-electrolytes. For them you take it as only one particle. Okay. And next thing is, look at here, urea is also non-electrolyte, I value is 1. And KNO3C, it can give K plus and nitrate ion, NO3 minus. So I value here it is 2. Okay. So now take the product of these two things. See, I value is 3. So delta TB I am calculating. Delta TB equals to I value is 3 into its concentration is 10 power minus 2 into, see, aqueous solution, it means the Kb value here it is same for all the solutions, because Kb value depends only upon the nature of solvent. I have discussed now, Kf, Kb depends only on nature of solvent. What is the nature of solvent? It is aqueous solution now. It means it is same in all cases. Kb value will be same in all cases. Okay. So Kbi, Kbm I have taken. Okay. So next thing is, so we have here 3 into 10 power minus 2. In this case, I can say 1 delta TB equals to 1 into, so I can write this as 15 into 10 power minus 3 or 1.5 into 10 power minus 2 Kb, like this. Okay. So out of these two, we know first value is greater, so that will be having highest boiling point. So when it comes to here, delta TB equals to, I value for this I told it as 1 and its concentration is 10 power minus 2 multiplied with Kb. Okay. And see, value it is lesser. For urea it is lesser value, delta TB value is less. For these, if you calculate, delta TB equals to, I value is 2, concentration is 10 power minus 2 into Kb. So now look at the values which is having highest value. The first answer is having more value now. So greater the ions, greater the I value, greater the Van 't Hoff factor, greater number of ions are formed, greater number of particles are generated, more is the colligative properties. Okay. So I can write answer in this order if I want to write perfectly. See, for this question you directly choose first option. If I want to arrange them in the order of highest to lowest, highest is for A, then next D, after that here 1.5, here 1. So after that B, and least is for C. So this is how you need to answer the questions. Hope it is also clear. Okay. Let me move forward. So the plot of, okay, we will come to this in the next session. So the next thing is, I just want to ask you one more easy question. See, which are the following pair of solution is expected to be isotonic? It means what? This is based on what? I values only. Here also, see, here also pi 1 equals to pi 2. Yesterday we discussed as isotonic, hypertonic, hypotonic. So now tell me, I value should be considered here. ICMST you should take here, and this is also ICMST. Here same temperature now, at the same temperature. So temperature removed. So S is a constant, you can remove both sides. So take the product of these two things of the given electrolytes and one which is having same value, that will be your answer. So for this urea I value 1 into 0.1, so this is 0.1 only, and here it is 0.1 into 2, so this is 0.2, so it is not equal, remove this. And for what about this? So I value for urea is 1 and it is concentration is 0.1, and here I value is MgCl3 now, so 3 and 0.2, so this is 0.6, this is also not equal. Okay. What about here? So this is 0.1 into 2 and here 0.1 into 3. Okay, this is also not equal. And what about in this case? We have I value calcium ion and nitrate ions. Total ions are 3, concentration is 0.1. Okay, it is 0.3 this side. And what about here? So total ions Na2, it means 2 sodium ions and 1 sulfate ion. So 3 multiplied with 0.1. So here also 0.3. So concentrations I into concentration, both sides are same. So I can say fourth option is having isotonic solution. Right now. So Hope this is also clear, right? So in the upcoming session I will be coming up with questions, numericals of this chapter, especially colligative properties, and live will be starts around 1:30. Okay, so just stay back with the channel. We'll meet again in that live session. Okay, so as of now I just wanted to ask you one more question. So how do you calculate alpha value, degree of dissociation, otherwise I value, what is the I value of an electrolyte, something like this. See, I am giving AB2 electrolyte. Okay, so this is an electrolyte, it dissociates something like this now, A plus 2 plus 2B minus. Okay, having alpha value as 0.6, alpha value is 0.6. Okay, or they will be indicating it as 60%. Okay, so they will ask us to find its Van der Waals factor. Okay, this is a question I am giving you. Now just give a try. In the next session, in the 15 minutes, I will be back with the numerical session on colligative properties. There we will discuss. Okay, find I value for this. Okay, so now what happens when dissociation takes place? This is a scenario we discussed, dissociation. Now what happens in case of association? I have A particles of n units. Okay, these are undergoing association to form like this. Okay, initially I have n particles at a time T0 initially, and this is 0. After some times it is undergoing association to form like n minus n alpha are decreased, and here it forming it as 1 alpha right now. So now from this what will get? Total number of ions, add this one plus this one, so it will be 1 minus n alpha plus 1 alpha. Okay, from this I can write, see what I am doing is I am just wanted to divide this with n. Here also I am dividing with n for simplification purpose only. So what will get? We will get 1 minus alpha here, because this is removed, and here we will get alpha by n. So total number of particles, now tell me, it is easy now. So 1 plus 1 by n minus 1 alpha. This will be the number of ions after association. If I want to ask this Van der Waals factor, so it will be number of particles before after association by before association. You can take it like this. Okay. So this is the formula you have to use for calculating Van der Waals factor for association. For dissociation I have given now I equals to 1 plus n minus 1 alpha d. This is alpha A, this is association. Both are important. Yes. So hope you will be stay connected with us for the next live session within 15 minutes. So stay connected with us. I will coming back. Okay. Thank you.